Hey guys, what's up? In this video, I will show you how to make a custom bird for your model and use the images we created in the previous video. You can watch it from the link on the screen if you miss it. Let's go! Okay. After that, we made our model in Blender. I'm gonna go to my Gazebo working space directory, which is it, workspace, inside the models directory. This is where Gazebo knows that I put my models inside it. So when I address the model inside the world file, if the model is in this directory, it will find it. To specify a directory as your Gazebo path, you can open your bashrc file and enter your password. Okay, sorry, I should put nano or whatever that you use to read your files here. You can put this line at the end of your bashrc file, so whenever your terminal you open a new terminal, this command will be executed. So Gazebo now knows this directory, my GZ workspace models and worlds, as its path, and I can put my models and worlds file there. Okay, inside this directory, I'm gonna make my new model directory. I'm gonna name it flying cylinder. Okay, I'm gonna cd to it. Okay. Inside every model directory, I need two files. I can make them with touch if I have it. Model.config, and model.sdf files. Okay, and I need another directory which name is meshes, I think. Yeah, gonna cd to it. Sorry. Okay, inside this folder or directory, I'm gonna put the AE or quality files that I made with Blender. So I'm gonna copy my files in. Dang, it was in this directory. Documents, Blender. Let's see if you press tab multiple times, it will show your options. Okay, you can see that I have my quality files here. I can them cylinder.dae. I can copy this here, and my propeller clockwise and propeller counterclockwise. Okay, now I have my quality files here, and I can use these files as meshes in my model or model.sdf files. Okay, let's write our model.config file. This is the file where we put our settings of the model here. You can find an example of this file in Gazebo's tutorial page. We'll use the same. We're using XML version 1, and our model name is this name is the name where we use it in our world files. In world files, when we want to include a model, we will include it with this name here. I'm gonna name it flying cylinder. This is actually version 1, SDF version. We're using 1.7. Author name is, you can put your own name, Lamson, or Lamson 2026 at gmail.com, and a description of a model. This is a flying cylinder with two propellers, 2 propellers, rotation only on z-axis. Okay, this is a config file. Okay, now we'll walk through our model.sdf file, which is describing our model flying cylinder to simulator, which is the gazebo. SDF file, or SDF, which stands for Simulation Description Format, describes our model's physical structure and geometry to the simulator. Actually, this file tells the simulator that how our model is being made and how its parts are connected to each other and how this will behave under physical forces and torques applied to that. And we'll walk through this file and explain that how our flying cylinder made up with links, joints, and sensors. First of all, at the beginning of this file, we should specify that this file is actually an XML file with its version, and the SDF tag, which contains almost everything. Then we'll create our model tag and the name of the model. This name should match the name that we gave it in our config file, and later in our world file, we will use this name to include our model to our world. Okay, the model tag, which is the most important tag, contains some settings, let's say at the first, and it contains mostly the links that which are the how can I say, every independent rigid, let's say rigid part of our model is defined as a link in our file. For example, our flying cylinder contains 3 links. First, the main body, which is the cylinder, the rotor 0 and rotor 1, which are the propellers. Inside every link, so this is the link of main body or the cylinder we made in Blender. We have to specify the position and orientation of our link in the word frame. Pose tag specifies the position. First 3 numbers of this tag are describing the position, and the second 3 are describing the orientation of our model. Then the inertial tag, which is the inertial properties of our model, and it actually has a pose, but I set it to 0, and the mass and inertia matrix. These numbers are not precise and not generated for our model. I just set them some arbitrary which are meaningful, are not so unreal, I say, are reasonable numbers, but they're not precise. But later we will actually generate and extract these properties of our model we made in Blender using other softwares like FreeCAD or SolidWorks or other softwares like this. But for now, we're just setting these numbers, some reasonable numbers, and go on with our simulation. Then the collision, which describes the main physical property and geometrical property our model, and how the simulator environment physics gonna see our model. For example, you can use some geometrical shapes as geometry here, but since we made our model in Blender, I'm using the Clady file of the model here as my geometry under the mesh tag. This address is the address that we put in the bashrc file. So when I address my file like this, like model / flying cylinder, it will search the the directory I gave it to. So, and the visual. I almost always make the visual and the collision the same in most of the parts, but I add some material and color for visual, so it can it'll be more beautiful to see. Here in material, we'll add 3 tags which are describing the material and color of our model. Ambient is actually the color, or actually the way we see our model when no any direct light is hitting our object. First 3 numbers are showing the RGB combination of color, and the last one is the alpha, which is describing how transparent our model is. Then the diffuse tag, which is how we see our robot when direct light is hitting to it. I almost always make them similar because I don't want it to change color when I have a direct light or not. And the specular, which kind of explains the glassiness of our model. As much as these 3 numbers are close to 1, it is more glassier, and as much as it is close to 0, it is less glassier. You can search for RGB of your favorite colors. I here just made some pastel light colors that I liked it, but you can make it different colors that you want. At the end, I added an IMU sensor to my model, and I'm gonna show you later in later videos that how we get our IMU sensor data. And here I named it my sensor, and the type is IMU. This is defined in Gazebo, so later you will see the structure of the message we are getting. IMU sensor is actually contains an accelerometer and a gyroscope. An accelerometer measures the linear acceleration of the body in 3 dimension, and the gyro is measuring the angular velocity. We'll use these data to estimate the position and orientation of our body as it moves, so it is critical and essential for control. Here I specified that my IMU sensor is on, and there is no signal needed to make it on. It is always on. And I set my update rate to 250, which is fine for simulation. But as you know that real IMU sensors in industry are much more update rates, something like around 1000 or 1200 rate, which makes it useful for industry stuffs. And I made it visible actually. And here, this one is very important. I specified the topic name. I'm gonna see my sensor output here. I can specify the name, so later I'm gonna call this topic, I'm gonna subscribe to this topic and see my IMU output. So you should be careful about this name and specify the meaningful one. Then we'll go on with our rotor link, which has some which is some then there is our rotor link, which is very similarities with our base link, but I'm gonna continue here. It is also has a collision. I added my counterclockwise propeller as its mesh and the visual, which are similar to my collision, and I added some color and material to it. But here I defined a joint between my base link and my rotor. These 2 tags here are specifying the parent and child of a joint. I specified my joint. I chose revolute joint, which is a simple joint, and it is a joint which is rotating around single axis, and this is what I need for my rotor to be like brushless motors of UAVs. I specified my base link as parent, which means that this base link is fixed and my rotor gonna rotate with respect to my base link, and this is very crucial to be specified. Then I specified the axis properties of my joint. Here I'm saying that my rotor will rotate around z-axis. +1 means in the positive direction of z-axis, and -1 means in the negative direction of z-axis. Then I specify the limits, lower limit and upper limits of my rotation. As you can notice, these are very aggressively small or large numbers, these limits. This is actually a trick that we use in Gazebo or maybe in other simulators to make our revolute joint a free joint, and it is able to rotate unlimitedly, like the real motors we use in UAVs. And the dynamics. In the dynamics, some joints have some spring like properties, but here in spring stiffness, when you set it to 0, you're saying that my joint is not like a spring, which is in our case is not a spring motor. Then here spring reference, we specify that our reference angle or rest angle for our joint is 0 in radians. If what is a rest angle actually? If our motor has some spring like properties, if we rotate it to some angle rather than 0, some force is gonna act against its rotation to bring it back to rest angle. So by setting this spring stiffness to 0, it's actually nonsense, and we don't have such properties for our motor. Then there's the damping tag, which specifies the amount of damping we will have on our motor. This is a very small number, but we specify it so so the simulator will have more stable numerical calculations. So this is good to have it, non-zero number, but I set it to very small number, so we're not gonna see much effect. This is actually damping of our joint. This is not the drag force that's applied to our propellers and stops it after we are not sending it rotation commands anymore. So this is different than that. Then I used this tag, use parent model frame. This specifies that when I set it to 1, it is telling the gazebo that my joint will rotate around the z-axis of the parent model, which is the base link, not the rotor itself. Why this is important? Actually, in real world, it's not like this. It is the propeller rotating around the motor z-axis, or the propeller z-axis, not the body z-axis. But in ideal case, we want our motor to create a thrust vector in the direction of z-axis of our model. So by setting this to 1, I'm just making things easier for me to have my simple simulation. Later we will change this and see the effect of rotating our motor's frame and see the effect on the base body. But for now, we're setting to 1. Then the rotor 1 is almost same as the rotor 0, but only the file is different because this is clockwise, and I used a different color for my clockwise propeller because I wanted to make it more distinct and visible. And the joint of rotor 1 is as same as the joint of motor 0. To make world file, first we change our directory to the Gazebo workspace. Actually, my Gazebo workspace. And inside the worlds directory, I should make my file. I'm using touch. I'm gonna name it Flying Cylinder World, SDF. Then I'm gonna open VS Code in this directory. Okay, now let's look at the world file. This file defines the simulation environment in Gazebo. It tells Gazebo which physics settings to use, which system plugins to load, and which models should be placed inside the world. Again, at the beginning of the file, we specify that this is an XML file and the version. Then at the top, we define the SDF version and the world name, which is Flying Cylinder World. Next, we configure physics. The physics engine type is ODE, which is one of the Gazebo's standard physics engine. The maximum step size is 0.004 seconds. This means Gazebo calculates the simulation in small time steps of 4 milliseconds. A smaller step size guarantees more stability and accuracy, but also more resource usage. And on the other hand, larger step size consume less sources but less accurate. The real-time factor is set to 1, which means Gazebo tries to run the simulation at the real-world speed. So 1 second in the simulation should match 1 second in real life. But this is totally depends on the hardware capability of your system. After that, the file loads several Gazebo system plugins. The physics plugin enables physics behavior like gravity, forces, motion, and collisions, and things like that. Then Scene Broadcaster plugin sends world and model information to the Gazebo GUI. Without it, the simulation may run, but the scene may not be properly visible in the interface. The user command plugin allows commands from GUI or command line, like moving models or interacting with the world. The sensor plugin, this enables sensor simulation. Here it uses the Org2 render engine, which is used for rendering camera-based sensors and visual data. Later, we will use camera and visual sensor for both odometry and detect and track projects. The IMU plugin enables IMU sensor updates. This is added because we have an IMU sensor in our model. Next, we include the models that we want them in our world. First, I added a sun model to give the world a light source, and then I added a ground plane model. This gives the simulation a flat surface. I positioned it on the origin. Okay. So far, the configuration is almost the same for all files that we write, except for the sensor section, which is actually depends on the type and number of sensors we used in our models. So it is very useful if you make a world template for yourself, and every time you want to create a new world, you do it by modifying the template. It makes things a lot easier. Okay, after that we include our main model, Flying Cylinder, which contains a cylinder and 2 rotors with revolute joints. And its pose is set to 0, means the model starts at the center of the world with no rotation. Okay, inside the Flying Cylinder include block, we add the motor plugins. These plugins connect Gazebo's multi-copter model to the rotors in our model. The first motor plugin controls rotor 0. It connects to rotor 0 joint and rotor 0 link. The plugin defines how the motor behaves. For example, the turning direction is counterclockwise, and time constant up controls how quickly the motor speeds up, and time constant down controls how quickly the motor speeds down. These are actually the accelerations. Max road velocity sets the maximum motor speed we can reach. The motor constant controls how much thrust the rotor produces, and moment constant affects the torque created by the spinning rotor. Here the drag and rolling moment coefficients are at more realistic aerodynamic effects, drag and rolling moment to our model. And we name our motor number 0 because this is our rotor 0. The command topic is Gazebo command motor speed. This is the topic where Gazebo listens for motor speed commands. After running the simulation, I'm gonna show how to send motor speed command to propellers in order to make our cylinder take off. The motor speed is also published to motor speed /0 topic, so we can monitor rotor 0 with this topic, with subscribing to this topic. Rotor velocity slowdown sim is used to slow down the visual rotor speed in the simulation, and both motors are using velocity control mode, which means we directly command the rotational speed of each rotor. Then we define the second motor plugin for rotor 1. It is connected to rotor 1 joint and rotor 1 link. Most of the parameters are the same as rotor 0, except that this rotor spins clockwise in the opposite direction of rotor 0. As I said before, using opposite direction torque helps balance the torque between the two rotors. And this motor publishes its motor speed to motor speed /1 topic. So overall, this workflow creates the Gazebo environment, loads the required simulation system, adds the sun and ground, places the flying cylinder model, and connects its rotors to Gazebo multi-copter motor system. Okay, after having our SDF files ready, I'm going to run my world with Gazebo. In this system, I'm using Gazebo Harmonic on Ubuntu 24. So to run my world, first I'm changing my directory to my GZ workspace in the world's directory. Here where I created my world file, oops, I misspelled flying here, so I'm just let me rename this file. Since we don't have directly renaming command in Linux Ubuntu, I'm using move this name to flying, yes, cylinder world.sdf. I hope it is correct this time. Flying cylinder, yes. So to run my world file with Gazebo Harmonic, I should enter gz sim and the name of world file. Paste it here and hit enter. You may have some warnings here, but it's okay most of the time. You can ignore them. Now you can see our model exactly like the one we designed in Blender with cute pastel colors. If you want to start the simulation, you have to push the run button over here. Now Gazebo starts to publishing and subscribing to topics that are specified in the config files. But before we start with the topics, notice that this is showing actually the real-time factor of simulation. As you put it to set it to 1, this is trying to keep it 100%. But as I said, this is completely depends on your system hardware capabilities, your CPU or GPU, if you have to run this software. Okay. Let's go on with the topics. Let me split terminal here, separate the terminal to work with our topics. To see the list of topics being published, you should enter GZ topic and -L for list. Then hit enter. These are actually the topics that right now is publishing by Gazebo. The most important one is actually the IMU topic, which is related to the sensor we added to our model. This topic is actually publishing the information or the data of our IMU sensor, and later we will use this topic to get the data of IMU sensor and estimate the position and orientation of our robot and use it directly in our controlling logic. So this is a very important topic. If you see what is the content of this topic, we should use GZ topic and -E, I think, for echo, and -T to specify the name of the topic, and paste your topic name here. Okay, as you can see, we are receiving the real-time IMU data. I'm stopping it here just to see what's happening. It starts from here. It has a header, it has a stem, which is showing the time of the data is published. Later we will explain these more because they're so important. And the orientation with quaternions actually, and the covariance and angular velocity and the covariance of angular velocity, which are so important. And it is actually calculating the linear acceleration, not with only yes, it is okay. Enjoy high school. And it is publishing the linear acceleration and the covariance of it. Yeah. We see what's going on with our IMU topic. If you remember, we defined a command, velocity command, or motor speed command topic in our Word file, so that we can send our velocity commands to our motors to make them rotate and produce lift and lift of our model. But we didn't see our topic here because this is listing the topics that are being published, not being subscribed. Actually, I see it here. Come on. Look. Okay. Okay, now we want to send the speed command, motor speed command to our motors so that they rotate and start rotating and create thrust and make our cylinder lift. If you want to publish a topic, first we should know the name of the topic. As you remember, we specified the name of our topic, Gazebo command motor speed, but we have to append the robot namespace to the beginning of our topic. So the topic name is Flying Cylinder Gazebo command motor speed, and we can see it in our topic list here. Flying Cylinder Gazebo command motor speed. This is a topic actually we have to publish to this, so our Gazebo model is subscribing to it. To publish this topic, before publishing it, we have to know the type of the message this topic is, so that we can define our commands in the format of that message. To see what message type it is using, we can use GZ topic and -I for info and -T to specify the topic name. I paste it here. Okay, now you can see the information of this topic. As you can see, there is no publisher to this topic yet. We will publish actually to this, but there are 2 subscribers to this topic, which are the IP and port are specified here, which are our motor joints. If you remember, we specified in our Word file. This is actually the type of the message this topic is using. I'm copying it. Now to publish this topic, we should enter GZ topic. I think it was -T and first specify the name of the topic. Okay, and then -m to specify the message type. And our message type is JZ message actuator, and then -p for publishing. This is if we want to publish a message in GZ message actuator type, we simply will type the data and colon and the number that we want to publish. For example, say 400. This is actually the runs per RPM that we're publishing to our motor. If we hit enter, okay, we have a problem here. Message type GZ actuator has no field name data. Okay, I actually made a mistake here. This error says that this type of message has no field name data. It is actually velocity, not data. So this was my mistake, and I have to make it. Okay, I'm copying, paste, and make the data velocity. I hope it is not with. It is with lowercase v. Okay, I think that I published it. Okay, as you can see, our propellers start to rotating. Let me set this always on top. Oops. Okay. Let's make this a little bit smaller so that we can see the rotation of our propellers even smaller than this. Okay. As you can see, our counterclockwise propeller is rotating in the counterclockwise direction, and the clockwise propeller in its clockwise direction. And it is as we defined in our SDF files, so it is working properly. If we want to make this thing take off, I think 800. Let's see if it is enough to lift off this. No. How about 850? Oh yeah, it starts to take off. Oh, this is really fun. Okay, let me reset my simulation. Okay, in next video, we'll use these topics and IMU topic data to control actually the movement our cylinder. So if you like this video and you want to see that simulation, please subscribe to our channel and like this video and wait for our video. I'm gonna use this topic to command to send the control command to my model and use IMU data to estimate the position and orientation of my model and make a control loop, complete control loop with these data. Okay guys, thanks for watching. If you liked the video, please don't forget to press the like button and subscribe to the channel if you want to see more videos like this. Bye.